So let's take a look at another way of doing the power delivered to the load calculation. And so in this situation, we have a voltage source with an RMS value of 110 volts and some load that has an impedance of 20 plus J20. Now, we don't know exactly the frequency coming out of the source, and we don't necessarily know what components are in the load, but for this calculation, we don't need those elements. And so a couple things to look at is what might be the real power delivered to this load and what might be the apparent power. And from that, we can start to figure out the power factor and then how much current would actually be delivered if the circuit was completely resistive. So we're going to look at several things in this, but to start with, we're just going to do the real power. And so when we're looking at this, recall that the real power is the IRMS squared value times whatever the real part of the load is. And so in this example here, the real part is just this 20 right here for the in the real component, and there's also 20 in the reactive component. So if we can find out the RMS current that is flowing through here, then we would be able to determine the real power rather quickly. And so the RMS current that flows through this circuit is again going to be the total voltage source divided by the impedance. And so this is going to be 110. And again, there's not going to be a phase to this object, so we're going to assume that the voltage phase is 0 because it's not specified. So if it's not specified, we're simply going to assume that it's 0, and this will be over 20 plus J20. So the result of this calculation here is going to be a polar value that is about 3.9, we'll say. Well, it's 3.889, but we'll round up to 3.9, e to the j negative 45 degrees. And so it's important to note that this is IRMS as a vector. This is a function. So this particular quantity here is the scalar IRMS, and this is the current phase. So we want to make sure that when we do all these calculations, we distinguish between this value of RMS and this value of RMS. But now we have enough to figure out what our real power is, and so our real power is going to be this RMS current value, so 3.9 squared, and then times the real part of the load, which is 20. And the result of this calculation is going to be that the real power is 302.5 watts. And so our values of R come from right here, so that's our R value, and 3.9 comes from right here. Now we're going to find the apparent power. Recall that the apparent power, which is just scalar S, is VRMS times IRMS. And we already know VRMS, the RMS voltage, as 110. The RMS current flowing through this is 3.9. And so the apparent power through this circuit is 427.8 VAR. So apparent power, or excuse me, not VAR, volts amps. So it's just volts amps for apparent power. And if we were to ask sort of how efficient this is, like what is the power factor? The power factor is the average power over the apparent power. And this is at about 707. So this is 70% efficient in terms of a power factor. This is actually a rather poor power factor. You generally want to be, about 95%. So between 0.95. So down here at 0.7, that means that to deliver all of this energy to the circuit, like it only ever consumes 302 watts worth, but then there's an extra 120 VARs that have to be delivered as the reactive power to make the circuit operate. And so in the context of this problem, if this was a motor, there's a lot of energy being exchanged backwards and forwards due to the motor that is just not being used to turn it, but is actually just causing it to be exchanged between the motor and the source. And to get sort of a better sense of that, like if this motor is only consuming 302 watts to get any work done, but you're having to supply it with 110 volts, in an ideal world, you would only send this thing 2.75 amps. So the real work being done, there's only 300 watts of work being done on a 110 volt source. And so truly only 2.7 amps are needed, but to make the circuit operate, you have to send 3.9 amps. So that extra current that is being sent by the power company, by whatever your power source is not being used. So there's about 1.2 amps that are just kind of wasted and get exchanged backwards and forwards between this load and then this voltage source. So only 2 amps or so are actually getting consumed, and 1 amp, 1.2 amps just keeps going backwards and forwards from the voltage source into the load itself.